we're going to take a look at what it means for a function to be continuous at both a point and on an interval. So if we think about what continuity means, that word continuity, if you looked it up in the dictionary even, continuity basically means unbroken, right? Continuous, continuous service, unbroken service. You didn't leave, you didn't quit your job, that sort of thing. So continuity means unbroken. So we're going to actually use that when we talk about functions and graphs. Okay? So if we want to take a look at continuity of graphs, we have two graphs here that are continuous for most of their graph. Okay? So we can ask a couple of different questions here. We can ask, what's this function f, and then we'll call this function g. So we can ask ourselves, is f of x continuous at x equals 1? So is f of x continuous at x equals 1? So if we use the idea that continuity means unbroken, the answer is no. Because in order to draw this, I would have to lift my pencil when I got to x equals 1 to leave that space for that, that dot that's left there, that hole, and then I can continue onward. Okay? We can ask, is f of x continuous at x equals 5? Okay, so here's at x equals 5. And the answer is yes, it is unbroken when I get to 5. So in other words, if I try to travel along the graph from the left side here, and I get to 5, do I have to lift my pencil to continue drawing the graph? The answer is no, I don't have to lift my pencil. It is continuous. So the answer is yes. Similarly for g, is g of x continuous at x equals 1? Well, you might say, well, it has a point at 1. Does that make it continuous? No, because what's the question? Do I have to break the contact of my pencil with the paper? And the answer is yes, in order to place that point at a different by value. So the answer here is this is not continuous. So no, it is not continuous at x equals 1. But is g of x continuous everywhere else? Say x equals 7? And the answer is, in fact, yes. We would say it is continuous at x equals 7. Okay. Let's look at a couple others. All right. This one in particular, let's talk about where it has continuities. Instead of asking, is it continuous at a particular point, let's discuss where is this not continuous. So where is, again, we'll call this top one f, and we'll call this bottom one g. Where is f of x not continuous? Or is there a place where f of x is not continuous? And the answer is at x equals 1, right? We've got a break in the graph right here at x equals 1. Alternatively, where is it continuous? Where is f of x continuous? You might see this asked as, on which intervals is f of x continuous? This is continuous everywhere, right? To the left of 1 and to the right of 1. So we could write that as for x less than 1 and x greater than 1. If you like interval notation, that would be negative infinity to 1 together with, union with, 1 comma infinity. Okay. Let's take a look at g. Another way to ask where is a function not continuous, we would say, let's see, instead of where is, let's say where does g have a discontinuity? So a function is not continuous means it's discontinuous. So let's see, where does it have a discontinuity? Well, it's got several. First, it's got one here at -4. It's got what's called a jump discontinuity because we have to, draw one part of the graph and then jump to the other part of the graph. It again has a discontinuity at -2, because it has a vertical asymptote. Okay. Then we have another one at -1. And that one has what's called a point discontinuity, or a removable discontinuity. It's removable because all I would need to do is take that point that's someplace else and fill it in. I can move it. Okay, I can sort of, I like to use the analogy of when you look at a wall, right, it's continuous. If it's flat, it breaks or holes in it or anything like that. If it's got a serious break in it, like this first half of this graph, or the first third of this graph, it has a jump in it. You consider that like a break in the wall, a big, big crack wall. That's not going to be fixed with a little bit of spackle, so it's not a removable, it's a jump discontinuity. If it can be fixed with a little bit of spackle, like a little hole, then we call it removable. It's easily fixed, okay? So at x equals -1, we have another one at 2. We have another one of those asymptotic types of discontinuities. So at x equals 2, and then last we've got another hole or removable discontinuity at x equals 3. So it says 1, 2, 3, 4, 5 different discontinuities. Okay. So there are a couple different reasons. So we've got this jump discontinuity. So that means we've got a limit from the right and a limit from the left at -4. So if we pay special attention here at -4, if we take a look at the limit as x approaches -4 from the left and as it approaches from the right, we get two different limits. Right? There's that jump. The one here in the middle at -2, the next one, -2, this is the limit as x approaches -2 from the right and from the left does not exist. So there's another type of discontinuity. So one type of discontinuity occurs when the limit is different from the right and from the left. The next type of discontinuity occurs when the limit is infinite or does not exist. The third kind is at -1 here. Now this time the limit does exist, but what's the problem? It's not continuous because the point is displaced, right? So here, it's not that the limit doesn't exist, it's that the function value is not the same as the limit, right? The point has been moved. Okay. And that's the other one. The last one is at x equals 3. We said that was another removable discontinuity. And again, if we look at the limit, it does exist, but the function value doesn't exist. Okay. So we would say this is continuous. G of x is continuous on the intervals. Let's see, we've got several here. So from -infinity to -4 inclusive, right, because the point is included there, together with -4 not included to -2 not included, together with, so that was that part there. Now we're going to do this middle part. So together with -2 to -1, then we've got that break, and then it picks up again and is continuous after that from -1 to 2. And then this last piece here, together with 2 to 3, and then from 3 to infinity. So we've got two different parts here, so I'll highlight those. We've got this part and this part are these last two intervals. So this is in several pieces, okay? So in these particular examples, we talked about a couple of different things. We talked about where a function is not continuous or where it has a discontinuity, and why it doesn't have why it's not continuous there, why it does have a discontinuity. So it can be discontinuous or not continuous for a couple of different reasons. One is the limit from the left is different from the limit from the right, as we had at -4. That the limit does not exist because it's infinite, as we have here at -2, we have an asymptote, and the limit does not exist because from the right and from the left, even though they both go to positive infinity, the function does not actually exist at -2, right? We can't actually say g of -2 is some number. It doesn't exist. Okay, that limit doesn't exist, or the function doesn't exist there. The next one is a removable or point discontinuity, and there the limit does exist, but it's not the same as the function value, so that would be the case here where the limit is 2, but the function value is -2. Okay? And then the last one was, again, a point discontinuity where the limit exists, but the function value doesn't exist. So let's take a look at a couple of problems. Here's a piecewise defined function. Okay, it has one function on the interval for x less than or equal to 1, and then a different function for x greater than 1. So the first part is to find f of 1. So f of 1 is equal to, well, first we have to figure out which interval it belongs to. Does it belong to x greater than 1 or x less than or equal to 1? It belongs to x less than or equal to 1. So that means part A would be 2 times 1 plus 5, or in other words, 7. Part B says, find the limit as x approaches 1 of f of x. Well, that means, let's see what happens from the right of 1 and what happens from the left at 1. All right. So if I'm coming in from the right, that means numbers that are larger than 1. So all of the numbers that are larger than 1, anything larger than 1, even 1.01, 1.001 would be in this x greater than 1 part, right? So we would use 4 plus 3 times 1. Oops. 4. Let's make that a little clearer here. 4 times 3 plus 1 would be 7. And as x comes to 1 from the left, that would mean numbers less than 1. So 2 times 1 plus 5 would be 7. So the limit as x approaches 1 of f of x is, in fact, 7, because from the left and from the right, they're the same. Okay, so we would have a hole in the part of the line 4 plus 3x. If we drew that line and then cut it off at 1 and put a hole there, it would get filled in. That hole would get filled in by 2 times 1 plus 5, and then the line would continue on as 2x plus 5. So the question becomes, is f of x continuous at x equals 1? Well, we said in order for it to be continuous, right, the limit has to exist. And in fact is equal to 7, and f of 1 exists, it equals 7, and these are the same. So in order for it to be continuous, we said the limit has to exist, and there can't be any holes, so the function value has to be defined there, or no asymptotes, and in fact our function is defined at 1, and in fact it's 7. And not only does the limit have to exist, and the function has to be defined, so limit exists means no asymptotes, no jumps. Function is defined means no asymptotes. But, as we saw, you can have a function have a limit and the function value exists, but they aren't the same. That's the one where the point has been moved. But this one, they are the same. As I described before, this first part, 4x plus 3x, we would draw that all the way up to 1, but then put a hole at 1. But 2x plus 5 takes over. And at 1, it is, in fact, 7, so the hole would get filled in. Okay. So, yes, this is continuous at x equals 1.